This is a production of the Chemical Education Material Study.
Here we see an acetylene flame, first in air, then with premixed oxygen. Acetylene burns to give carbon dioxide and water. The atoms in the reactants have rearranged to form the products. The bonding has changed and energy is released. Chemists explain this energy release in terms of these changes in chemical bonding. When heat is released, the bond energy of the products is lower than that of the reactants. To explain the heat release, we must understand why chemical bonds form. We shall consider the bond in the simplest molecule, hydrogen. This apparatus permits us to introduce H2 molecules into a discharge tube to convert them to hydrogen atoms, and then study the regeneration of hydrogen molecules. After adjusting the gas flow, the voltage is turned on. In the glow region, the bonds in the H2 molecules are broken to form atoms. We know hydrogen atoms are there because their characteristic colors of light are emitted in the glow region of the tube. This light emission is caused by high-energy collisions with electrons. As the gas flow carries the hydrogen atoms beyond the discharge region in the tube, the atoms no longer glow. In the path of the hydrogen atoms, we've placed a piece of fine platinum wire. We see that where the atoms strike the wire, it becomes white hot. Heat is being released. In animation, we can see how chemists picture what is happening on the platinum surface. Hydrogen atoms strike the surface and sometimes become bonded to it. When two hydrogen atoms approach one another on the surface, they can bond to each other and form a hydrogen molecule. The platinum has acted as a catalyst, and it is heated by energy released as the molecules are formed. The net reaction is H plus H gives H2 accompanied by the release of energy. A chemical bond is formed. Chemists explain this bond formation in terms of the electrostatic interactions between the electrons and nuclei in the two atoms. Their explanation makes use of the quantum mechanical view of the atom. Let's review this model. Here are two different ways we can represent the hydrogen atom. Each has its advantages. Neither way serves all purposes. The view on the left shows a possible position of the electron relative to the proton. However, it does not indicate that the electron changes position, which it does. On the right, the probability view of the hydrogen atom indicates how the electron occupies the space around the nucleus, but does not indicate where the electron is at any particular instant. The relationship between these two representations might be compared to the relationship between these two tops. The two tops are mounted so they won't fall over. They're both spinning rapidly, so we see only blurred views of them. But suppose we suddenly stop one of the tops. Now we can see the pattern on the top. We can see the orientation of the pattern, just as it was at the instant its motion was interrupted. At another instant of time, if we stop one of the tops, we find a different orientation. The spinning top gives a blurred or time average view of all orientations. The meaning is the same in this view of the two hydrogen atoms. They are blurred or time average views of the atoms. If we could suddenly photograph the atom, we would see that each consists of a proton and an electron. The electron positions are now visible. At another instant of time, a photograph would show the electron positions to be different, in accordance with the probability meaning of the orbital. This, then, is just a typical view of an atom. It has the advantage that we can discuss the electrostatic interactions between the particles. Here in this hydrogen atom, the proton and the electron attract each other, as do all oppositely charged particles. Work must be done to pull them apart, raising their potential energy. As they come together, the oppositely charged particles attract each other more and more strongly. The potential energy drops more and more. These are the types of interactions that must account, somehow, for chemical bonding. In each atom, the proton strongly attracts its own electron. When the atoms are far apart, there are also weak attractions between each electron and the other proton. Finally, there are weak repulsions between the two protons and between the two electrons. From these interactions, we must find why the energy is released when the atoms form a bond. The attractive forces, in yellow, are the ones that tend to lower the energy as the atoms approach. At very long distances, each electron is held near one proton. As the atoms approach, however, the new attractive interactions become appreciable. Potential energy is lowered. As the atoms move still closer to each other, each electron is now strongly attracted to both nuclei. The potential energy continues to decrease. The repulsions, in white, also increase as the atoms approach. These tend to raise the potential energy. However, at this distance, the attractions exceed the repulsions. This is so because the electrons can occupy positions between the nuclei, so the electron-proton distances are shorter than the proton-proton distances. Also, the electron-proton distances are shorter than the electron-electron distances. If the atoms approach too closely, the proton-proton repulsion becomes stronger than any of the other interactions. That raises the potential energy and causes the atoms to tend to move apart again. There is a distance at which the energy is a minimum. At this distance, the forces of repulsion, in white, just equal the forces of attraction, in yellow. The opposing electric interactions just balance each other, and the energy is a minimum at what is called the equilibrium bond distance. Now, let's examine more closely the energy changes that take place as two hydrogen atoms combine to form the molecule of H2. Looking again at the interactions between the two atoms as they approach, we can record graphically the total energy, plotted as a function of the proton-proton internuclear distance, r. When the hydrogen atoms are widely separated, the energy is just that of the left-hand atom, E sub h, plus that of the right-hand atom, again E sub h. The sum for two isolated atoms is 2 E sub h. As the atoms approach, their potential energy becomes lower, like that of a ball rolling down a hill. At the equilibrium bond distance, the potential energy is lowest. If the atoms are forced into shorter distances, repulsion dominates and the energy rises rapidly. The atoms separate again and seek the position at which the energy is lowest. We have now a model that explains the bonding between the simplest kinds of atoms, hydrogen atoms. A chemical bond forms because the energy is lowered as the atoms approach. The lowering of the energy results from the simultaneous attraction of each electron to two protons. Of course, we must be reminded that the electrons are in motion. These are highly probable electron positions. At another instant, the electrons would be found at other positions. The energy at the equilibrium bond length is the average for all electron positions at that bond distance. This average includes small contributions from some arrangements with one of the electrons far from both nuclei. It includes large contributions from arrangements with the electrons close to both nuclei. Now let's examine the interactions present when two helium atoms approach each other. Again, we use the instantaneous photograph representations of two helium atoms to examine the electric interactions. Each helium atom has 2 protons in its nucleus and 2 electrons in its 1s orbital. Keep in mind that these electrons are in constant motion, even though we show them as they might appear at an instant. In each helium atom, the 2 electrons are attracted to the 2 protons in the nucleus. But the 2 electrons, both of which are negatively charged, repel each other. Again, yellow for attraction, white for repulsion. Now, when 2 atoms approach each other, new attractions between the protons and electrons of opposite atoms become significant. But, as before, the new repulsions also become larger as the 4 electrons and the 2 positively charged nuclei approach each other. There are more and larger repulsions present when 2 helium atoms approach than when 2 hydrogen atoms approach. As the atoms move closer together, both the attractions and repulsions grow even larger. Are the attractive forces strong enough to lower the potential energy and form a bond? We must appeal to experiment to find the answer. Let's pass helium through the same apparatus we used earlier. When we turn on the voltage, again, collisions with electrons cause the helium atoms to emit their own characteristic light while they are in the glow discharge region. As the gas flow carries the helium atoms over the platinum wire, we see that the platinum wire is not heated. We see no evidence of energy release. Other experiments confirm that 2 helium atoms do not form a stable chemical bond. In helium, therefore, the attractive forces do not dominate over the repulsive forces sufficiently to hold the atoms together. Calculations show that if 2 helium atoms approach, the energy is lowered very little and only at quite long distances. Quickly, the repulsions become dominant and the energy rises. The atoms separate and no chemical bond forms. Our question of why chemical bonds form has now been at least partially answered. Starting with this hypothetical instantaneous view of the hydrogen atom, we examined the electric interactions in each atom. Using this model, we found that new attractions and repulsions become significant as the 2 atoms approach each other. As the atoms approach even closer, a distance is finally reached where the forces of attraction just balance the forces of repulsion, and the energy is a minimum. This distance is called the equilibrium bond distance. Finally, we saw that the attractions of each nucleus for the electron of another atom caused the bond. All chemical bonds form because of the simultaneous attraction of 1 or more electrons to more than 1 nucleus. This understanding of the simplest chemical bond in hydrogen applies to all chemical bonds. It provides a basis for understanding the energy effects in all chemical reactions. In this and all flames, heat is released because average bond energy increases. So 4 CO2 molecules plus 2 H2O molecules must have a stronger set of bonds than 2 HCCH molecules plus 5 O2 molecules. What do you think about the bonding in molecules of oxygen, O2, and methane, CH4, compared to the bonding in their combustion products, CO2 and H2O?